So welcome back, everyone. So the last lecture of 2020 for this class, at least. So I'll still host a review session. So next Monday, but this is the first lecture, so this is the last lecture with new material in the in the course. So thanks all for coming. It's been kind of an interesting semester, but I think we mostly got through it okay. I know for some people it's been rough, and so for a lot of you, I think you've done great. For those of you who are getting by, keep hanging in there. We still actually have about 1/3 of the grade is still out. You can still about the last homework assignment, if you drop a different one, is worth 15% of the grade, and the final is worth 20% of the grade. So if you do well in the last ones, the grades in the class can still go up. So I think everyone's still in the zone of passing. So great. And I think we've learned a lot this semester. So if you look at the schedule, kind of we started with kind of some revisiting some fairly basic stuff in probability and linear algebra, but we kind of use those to kind of understand models of data, both in terms of how to think about how the statistical ideas behind a model, and the linear algebraic ways to think about kind of representing data as vectors. Hopefully this is starting to become, or at this point, you're somewhat comfortable with this way of thinking, right? So hopefully you've become accustomed to this way of thinking. And then we've kind of gone through these various kind of core techniques within data analysis. We've seen linear regression, dimensional reduction, clustering, and now we're doing the classification part of the class. And so you kind of get the sense these are the four main kind of approaches within data analysis. There are other parts we haven't been able to touch. The whole idea of using graph-based data, for instance, isn't something we've done, but we've kind of viewed a lot of the core things here, and I've hopefully brought to you you've seen a core algorithm within each of these techniques. You've kind of understood how these probabilistic tools of modeling data, how to think of a model in this way, and kind of how to represent stuff as high dimension and vectors kind of should make sense within these approaches now. And you've seen kind of all the very most basic models, mostly the ones based on the sum of squared errors, motivated again from the kind of the Gaussian noise models. And then we've gone beyond those just a little bit. So this is kind of the introductory course in this area, and there's a whole bunch of cool courses you can take after this. I've been meaning to post something on Canvas or in class. So I'll try and summarize a bunch of the classes you can take in the next steps. Most obvious ones would be the machine learning and the data mining courses. The AI course is also great and builds on this natural language processing course. Next spring, I'll be teaching a course on the ethics of data science. First time I'll have taught that course before, but it's been offered for a couple years now. I think that's kind of super important topic. We haven't really gotten a chance to touch on that much in this course, but it's a really important area. So you're kind of creating solutions instead of problems with all these techniques. And then there's a couple of courses on deep learning, which will be offered in the spring also. The CS and math department offer one. This is usually in the falls, but there are a couple of ones, one for image analysis and one for biomedical informatics, which will be offered. And it sounds like after this course, you should be ready to take those courses. So I'll try and post some information about those as well. But this kind of, hopefully this is kind of a gateway course into this area. And we kind of designed this course from experience in teaching the data mining machine learning course, and these are kind of the core tools you need to get ready. Oh yeah, I didn't mention gradient descent. This is kind of the core algorithmic tool that's behind most of learning and data analysis. And you've kind of, homework 4 that part was tough for a lot of people, but that is kind of the the central thing that is done with most of data analysis, kind of gradient descent to learn a model based on data. And you now have an example of having done something like that, which is awesome. Okay, so if you look at the schedule, it's mostly up. The homework 5 is going to be due on Friday. Okay, so Friday at midnight, and that's so we can hopefully get that graded and back to you before the final exam. Final exam is the following Friday. The exam will be out most of the day from like 9 until midnight. I think I posted you'll have 2 hours to do it, and I'll be on Zoom from 1 to 3 for any quick feedback. So I recommend you take it then in case there are questions. I'll try and be available on Canvas and email at other parts of the day, but the feedback won't be as quick. Okay, and then I'm going to do a semester review where I'm going to go through the practice problems or any other questions, but probably think of an hour and a half until about 4, starting at 2:15. So I was going to start at the regular time, but I had something else get scheduled then. Okay, so next Monday, and I'll try and post it on YouTube as well as you can't make it. But if you look at this practice exam here, this is going to be harder and longer than what the final exam is going to be, which will be on Canvas. But it gives you a good and even bigger breadth of the sort of questions we're going to ask. Okay, so I recommend you try and solve these problems before you go to the practice review session, so you can try and do them before you see the answers. It'll give you a good sense of what you remember, what you don't remember, where you want to study. It might not cover every little thing that's going to be on the exam, right? But it's going to give you a good sense of the areas and have you recall those topics. Okay. So great. So any kind of last questions on the schedule and how we're going to wrap this up? Kind of, you can ask me anytime during this lecture on Canvas, but your last kind of official interactive time to ask me any questions about this. So great. So okay. So let's get to the lecture. This lecture will be on, the most part will be on neural networks, but I just kind of want to start by kind of reviewing the landscape of algorithms for classification, which is like most of machine learning. And we'll go through a couple of other options, and then we'll talk about neural networks, which is kind of the basis of deep learning, which is kind of this big, exciting area. And I'll try and highlight it's not the only thing going on. It's just that there's there's been these really wonderful frameworks built like TensorFlow and stuff that makes this sort of advanced, complex sort of learning for lots of data accessible. Kind of in a similar way that kind of MapReduce, if you, I don't know, maybe you're too young to know about MapReduce somehow, but if that MapReduce made kind of big parallel computing on big data kind of accessible to lots of people. So classification, right? Again, we're starting as the input is going to be a subset. Again, we'll say X is going to be in a subset of RD, right? X1 through Xn. And so within deep learning and other places, sometimes the input is going to be language, a bunch of text or images or other stuff. They typically first convert it into RD in some way. And the data mining class or the machine learning class may talk about some of those mechanisms, but this is still a fairly reasonable way to start here. And then there's also these labels, Y, which is going to be an element of Rn, right? Oh, sorry, I did the same thing last lecture of -1 + 1 n. So these are going to be each data point comes with either minus or +1, okay? And the goal is going to be a function G, which is going to go from the same place, the input of your data, to the real numbers, and you want the sign of G of xi to be equal to yi, right? So -1 or +1. You kind of want this to match. Okay, it's easier to work with functions which are continuous because we're going to be optimizing them typically with gradient descents. Okay, and so far we've looked at, and this is going to be true. We're still going to do this for the other types of learning. So far, this has been the case. We've looked at these linear G of alpha of x, which was basically alpha times x, maybe plus an offset alpha 0. Maybe this was, we used this as some normal vector, and you can think of this as an offset here. Okay, so this was the first thing we learned about. We talked about the perceptron, for learning this, or just you put on a loss function like the hinge loss, and you run gradient descent over this. Very similar to what we did with regression, but we changed how we measure the error. Okay, and then the last lecture, we again basically talked about a function in a similar way, but now the function looks slightly different, where we had an alpha j to xj, not to xj here, but to a kernel, and let's make this some data point p, right, from kernel from each data point here. So now we can do this with the linear function. This is going to ends up being somewhat equivalent to this linear formulation, but we could use a nonlinear kernel here as well. So we can do a kernel version of this, and this is nonlinear, and it would still often have some sort of offset here. Okay, and this allowed us to do nonlinear stuff. Okay, but what was similar with this, so you could think of that we had these plus data points and these minus data points, and the linear function did something like this, which did as good as possible, but maybe couldn't classify everything, whereas the nonlinear would allow us to find a decision boundary like this that maybe could classify all the data points we have, or the training data points we have, exactly here. And this can still be optimized. So this can still be optimized with gradient descent. In fact, this is still going to be convex. Okay, once we've written this as a kernel over all of the data points, then we basically treat, right, this term ends up being kind of a constant in the gradient formulation, and we can take derivatives with respect to the alphas the same way we did before, pretty much the same way we did with the linear case. So we can still optimize this. It's still convex. So everything we learned about gradient descent, that it's going to converge to a local minimum efficiently, or to the global minimum efficiently, was still true. We're just learning a different class of functions here. Okay, so what we're going to see today, I'm going to first show you a couple of different ways of defining these functions that are going to take different forms. And then we're going to go to neural networks, which are again going to be something we can optimize over again. Okay, the first two, we're going to talk about K&N classifiers and then decision trees, just very quickly, just to give you a taste. These are not things you really optimize. Okay, these are things that are just, you kind of optimize decision trees, but or at least random forests you do, but it's going to be a very different way of thinking, kind of like how this mean shift clustering was very different from the other sort of clustering we were talking about. Okay, but neural networks are going to be like this again. We're going to be able to write down a much more complex function but we're going to be able to write down all the parameters, these alpha parameters, and optimize over those again. And so we're still learning something, but it's not going to have all the nice optimization properties, but we still do it anyways. It's kind of going to be the punchline. Okay. And I'll try and give some insights into why these still work. And these are still fairly fresh ideas. We're still understanding this a little bit from the research side, but they definitely work. That's kind of the important point. Okay, so let's start with a couple of these other classifiers, and I'll just spend a couple of minutes on each of these. So Knearest neighbor classifiers. Okay, so this is a classifier that works very differently than before. There's not going to really be a decision boundary. You could probably draw one, but it's not like really apparent here. And the idea is you're going to have these data points. Okay. Okay, and they could be in some weird configuration, right? You have some positive points, some negative points. Okay, so you're given the input the same way. Okay, and so you're given now your input. Input is going to be X and Y, the same as before, and some notion of distance, D, which is kind of goes from so some notion of distance, which goes from, say, RD to R, right? So one of these distances we've talked about kind of earlier. Okay, and then we're going to get a new data point. Let's move it. Yeah, so let's put this new data point here. Okay, so this is a new point P, and I'd like to predict whether P is going to be negative or is positive, right? I'm not going to draw a decision boundary here. What I'm going to look at is I'm going to find this data point, and I'm going to find the closest K neighbors, okay? So find closest K neighbors, and we'll do an example with K equals to 5 here. Okay, so I'm going to find the closest other data points. And so this is my space RD, it's R2 in this case. This is the closest point, the second closest, the third, kind of the fourth, and maybe the fifth closest point here. These are the 5 closest points. Okay, so I can think of there exists a ball. I can draw around here that only contains the smallest ball that contains 5 points. And I want to look at all the points inside of here. And I want to count that I'm going to have 3 minus, and I'm going to have 2 plus, and then I'm going to take the majority. This is the majority. There are more minus labeled points among the nearest neighbors than there are positively labeled points. So I'm going to output -1. Okay, so I look at the nearest neighbors, and so I use those to try and make a prediction based on voting, right? So it's like you have look at the 5 most similar, or K in general, most similar data points you have, and then I vote to see how many are negative, how many are positive, right? If I were to instead pick some point kind of over here, I may have like 4 or 4 negative, right? Or over here I'd have 4 positive. That I'd be even more sure about my decision. Here it's kind of in between, but I'm going to vote and take this majority decision. Okay, so when you have kind of separable points, right? One of the examples we had, say down here at the bottom, right? That I use on the other classifiers, the results are going to be fairly similar here. But this is more powerful in that I can take as input kind of any sort of distance here. It doesn't actually need to be defined over our d-dimensional vectors. This could be defined over text or I've been working this recently where you have some curves, you've traced some trajectories of people and you measure distance between curves, and this is all you need when there's maybe not a good notion to map it to points in RD, then you can use this as your classifier. Okay, I didn't really do any learning here. I didn't build any classifier. Maybe I could have chosen this value K with some cross-validation or something, but I didn't have to really optimize over anything here. And this is a way of having a classifier function. Okay, so it's just a very different way of thinking about classification. Okay, so any questions on canon classifiers? Kind of hopefully fairly intuitive. Right? So a different one I want to talk about, just to give you a different sense, decision trees. Okay, so this, hopefully, as a computer scientist, the idea of a tree as a kind of a data structure would be so not something that's too foreign to you. Okay, but let's here think of so we have I wanted to make that red be consistent. Okay, so I have some points and some strange kind of configuration, some positive and some negative points. Okay, let's look at this example here. Okay, and so what the decision tree is going to do is going to build a sort of a binary tree on top of this data. If you've heard of a KD tree data structure used for kind of nearest neighbor searching, I don't know if you see that in any of your classes so far. We'll talk about in the data mining class if you haven't. But this is going to be like a KD tree built on top of here, and I'm going to build these decisions on the actual coordinates now. So I'm going to kind of draw these decision boundaries. Okay, so I'm going to start with this decision boundary, and it has to be either, usually the way they do these, that it has to be along the x coordinate or the y coordinate. And the advantage of this one is that now my notion of the coordinates I'm using don't need to have the same sort of units. Okay, before we had these issues with these, like I'm measuring height versus weight, right? In a single distance that didn't really make sense. Now I'm making a decision on either height or weight, but I'm not combining these ever together into a single kind of way of cutting them. So I don't really need to worry about if they have different units. In fact, I can use say categorical data as part of this one, right? So I can use categorical data here in a seamless way, or data which is kind of, some is real values like a height or weight, some is binary values like, are someone's eyes blue, or are they brown, or are they green, as listed on the driver's license. I guess it's not quite binary, but so you can use things like this without having to worry about kind of how to blend these together. Okay, so I first make a decision like this, and this is maybe among the splitting on the y coordinate, the single best way I can split them to kind of balance these things. And there are some various ways I'm not going to get into how do you decide how to do these splits. But then on the second thing, but then I want to make a split in the x direction. And so I might, actually, let me move this one over here a little bit. Okay, just so this is a little bit more interesting. Okay, so now I want to make a split in the y direction here, and I might do different on the top than I did in the bottom, right? So the top half, I want to say, well, I can do better splitting it left and right over here on the top half. Now, this top right quadrant up here is all positive, which is good. So if I made a decision on the y coordinate and then on this x coordinate, I can hopefully be pretty assured that everything up there would be positive. And I have a little trouble doing the same thing on the bottom part over here. Okay, now I've okay. So what I might do is a decision like this, which does pretty good, but I haven't quite classified everything. So then I'm going to make another split in the y coordinate again. Right at this point, now I've got this is also all positive, and everything else is going to be negative. Okay, and I can think of this like a binary tree where this guy is the root, this is the child, you know, and child of the root is this decision, and then this one also has another child in this tree. If you look in the yeah, so you could think of this as a binary tree, and I make a decision as I walk down from the root, and at some point I stop. And I might stop before I perfectly split one of these things. And there are various kind of, let's say, information theoretic ways to try and make the decision of when to stop. Okay, but I would train these decisions in this way. This is a decision tree. And it's, again, a very different sort of model. This one can handle things like when you have mixed types of data points for each of your coordinates. Okay, so this one is also quite explainable in that I can really explain a decision. And decision trees have long been pretty popular in, say, biomedical research, because when you need to kind of explain something to, say, a doctor, how did I come up with this assessment of whether I think someone is high risk or low risk for something like this? They really wanted an explanation, right? They're like, no, you have to tell me why you made this decision. And here you can say, well, I split the y coordinate, say they're above this age, they're put in high risk, but if they kind of run marathons or something, then they're non-high risk, right? And that was a second sort of category that you split on in order to split these. And often you can do this in high dimensions. You need to choose which dimension to split and then where to put the split point. And there are a bunch of details that go into this. Okay, these are often, they often don't work. They don't quite generalize quite as well as, say, the kernel SVMs and these other approaches. But there is this this kind of extension called random forests, okay, which is you learn a bunch of decision trees by effectively withholding some of the variables every time you do learning, and then you kind of blend them together. You kind of take you learn a weighted average of them in some way, and this is a kind of a non-convex process. But people have figured out how to optimize these. XG boost, was it XG boost, for instance, is an example algorithm for learning random forests, and these typically work kind of as well as most of the deep learning approaches in a lot of tasks. There's certain kind of highly structured settings where deep learning does better for various reasons, but in a lot of the Kaggle competition stuff, these are some of the best classifiers. These based on combinations of these decision trees called random forests, right? So it's a bunch of trees, that's why it's a forest, and there's some randomness involved, right? Okay, so this is a whole other branch of types of classifiers that I just want to give you a little bit of intuition about. Okay, great. So any other questions about decision trees or random forests? There's much more going on here, but I'm not going to go into all the details here. So great. Okay, so let's now go on to explain the rest of the lecture. I'll try and explain what are neural networks and how do we learn on neural networks. Okay, and this will start with the idea of a single neuron, and this is going to be a component of a neural network. And okay, it's gonna kind of look, and this is initially kind of modeled on how a neuron works in the brain, right? The brain is made up of these kind of little things called neurons that work with electrical signals in some way. And these neurons are effectively kind of modeled based on these, or at least that's where the name comes from. Okay, and the idea is to a neuron, okay, is that there are lots of things that where it can get some sort of some sensory input. Okay, so there's this big connected network of these in your brain, and I think we're trying to replicate that maybe in some ways, and it's getting input in some way. Okay, and it's taking this input, and we're going to call these input x1, x2, x3 up to say xd. Okay, actually, so that means that this is a vector. The input we'll think of as a vector x, which is a vector in RD. Okay, and so effectively, how does a neuron work? Well, it takes these, think of these as firings, electrical signals, and it takes some sort of effectively a weighted average of these. Okay, so think of this as it's going to be getting these signals, and there's a weight it's putting on each of these. Okay, and this is all going to be aggregated in some node here. And I'm going to take a weighted average, and remember a weighted average is going to be this, the sum equals 1 up to d, or I'll say j up to d, of each of the input values, xj, times a weight, wj. The weight could be something like 1 over d. If it's a uniform weight, it's just counting kind of the total amount, then it's just weighing them all the same. It's then each, so the uniform would have wj equals 1 over d, but it could be some other sort of weight. Okay, so this is the weighted average, right? So this is what is going on at here. Okay, and then it makes a decision. Okay, it's going to do some thinking and decide, is this greater than some threshold B? Is this greater than some threshold, right? I'm going to look at this weighted average. Is this greater than some threshold B? Okay, and if it's greater than some threshold B, then it's going to either output, say, -1 or +1. Okay, if it's greater than some threshold B, it'll put out +1. If not, it'll put out -1. And think of this as in a neuron, it sends another electrical signal downstream. There's kind of some thresholding that goes on. It's not just taking an average that kind of just ends up, if you keep taking averages of averages, you're doing central limit theorem and everything just kind of is a big mess. But there's some thresholding that happens at these neurons is what's happening. It's taking a bunch of signals, it weights them in some way, right, based on the strength of the connection. The stronger the connection, the more it weights them, right? And then it's taking and then it sees if it crosses a threshold. If it gets enough signal, it crosses some threshold, some switch flips, and it sends off another signal. That's a +1. And if not, it's a -1 or maybe a 0, you can think of it. It's no signal is sent out. Okay, so this is basically what is a neuron. And hopefully, the way I've written it with the notation I've used looks familiar to something, right? This is, I can rewrite j equals 1 to d of xj, wj is greater than b. This is equivalent to x w dot product, that's a dot product, minus b is greater than 0. right? And this is just a linear classifier, right? This is exactly a linear classifier, right? And I'm learning, what do I learn? I'm learning these weights. If I can learn those weights, okay? Okay, we talked about a couple algorithms to learn these linear classifiers. One is with a kind of gradient descent with a loss function. I'll come back to that. But the other way we learn is with a perceptron algorithm, right? The perceptron algorithm, what did that do? Well, it saw examples of things which were misclassified. And the way the neuron might work is a little bit different, but it only saw, neuron you think only sees positive examples. If it sees things where it sends a signal, then what it does, every time you send a plus signal with something, you go back and you strengthen the weights that were correspondingly big. If you saw something that can generate a signal, you made these weights a little bit stronger, right? So if I saw a data point that had signal in x1 and x3, and this generated a +1, I would effectively make those weights stronger. If I saw something, say, with x2 that did not create a +1 at the output, did not cross the threshold, I might make that weight smaller. That's kind of like subtracting it, right? And this is kind of how the neuron in your brain works. If it builds and grows connections, and if those connections successfully pass on the signal, it strengthens those connections. And if it doesn't, it kind of weakens those connections. There's some biological working that kind of works like this, and this is kind of the idea how this aligns with the perceptron algorithm, which we learned in class. The history of this, I think the perceptron is actually older than the understanding of a neuron, and this naming came afterwards. I'm not as confident about the exact history of these things, but there's this connection is kind of, there's some truth to this kind of connection. Okay. Okay, so does this kind of make sense as a basic idea of how to learn? And this I'm going to call neuron. And what a neural network is going to work in some way that we're going to kind of think of this as kind of a single object inside of here, right? We're gonna have a whole bunch of these neurons, right? Inside your brain, there are a lot of these. There's lots of these neurons arranged in some way, and they're all doing their thing as stuff is firing in there. And so, similar way, a neural network is going to have, instead of just one linear classifier, we're going to have a bunch of these stuck together in some way. Okay, so that's kind of the basic idea here. There's a few more layers of complexity. Okay, so all right, so how do we stick these all together? Okay, so a neural network, okay, and we're going to start to deviate a little bit about how the brain works in this way. And that neural network is almost always going to have be organized in this sets of these layers. Okay, so I'm going to have the input vector x, right? This is going to be an element of our D. Okay, and so I'm going to put a neuron on top of here. Okay, and I'll put a neuron. The first thing I'll do is I'll put a neuron on the top of here, and this will give me some. It's going to output to something, and we're going to call this. What do I want to call this? We'll call this H1. Okay. In fact, we'll call this H1I. Okay. So this will give me one output, and inside of whenever I draw one of these kind of these red triangles like this, this means there's going to be secretly inside of here. There's going to be these these lines, right? All these weights inside this triangle. Okay. Okay, but so the idea is I'm not going from my input, I'm not just going to learn one neuron here, but I'm going to have a whole bunch of these outputting different things on the end. Okay, and I'm going to learn from H1, 1, H1, 2, down to H1, let's say K. Right, so I'm going to learn a whole bunch of these outputs here. Actually, I'm going to call this, what I want to make sure my notation is, let me call these A, H is going to be the next thing, sorry. Okay, so let's call this A11, A12, I2 in general, and this is A1K. Okay, so I'm going to learn each of these things. So I'm going to learn a set of these outputs, and each of them is going to have D different weights, right? So I'm going to have, so far inside of here, this is going to have K times D weights here. Okay, so instead of taking a dot product, I'm going to basically do a matrix multiply, right? A dot product is multiplying by a vector. Taking x times a vector, I'm going to output a single scalar value. Now I'm outputting a vector. So this is a matrix multiplication. Okay, this is, I'm going to have weights, 1, 1 up to dk. And this is matrix 1. And I'm basically going to do an A1 is going to be a vector, a k-dimensional vector, which is going to be W times X. Okay, so I'm going to learn a whole matrix of weights now. Okay, so I'm learning a bunch of linear classifiers. You can kind of think about that. I'm not really talking about how I'm learning them yet. This is just the structure. Okay, but these are just the weights so far. I haven't figured out how to do thresholding. I want to do a threshold to be -1 or +1, right? And I want to stick more neurons on the end. I want to feed these neurons into the next neurons, right? And I want to get a chain of these in some layers. But I need to do a thresholding in between. The next neuron, each of these outputs here needs to decide if it's going to fire or if it's not going to fire, right? So I need some other element here in order to get this. Okay, and so this is going to be what's called an activation layer. Okay, so the next thing I'm going to do here is I'm going to pass this into, we're going to call a phi function. Okay, and the output is going to be H11, H12 up to H1K. Okay, and this will be a hidden layer. This will be the first hidden layer. This will be another vector in RK here, but it's going to have this activation. Okay, so phi is going to be an activation function. Okay, and this is going to kind of map from, so phi is going to be a function that's going to go from the real numbers to, well, I'd like it to kind of go to maybe -1, +1, but I'm going to need to optimize it again, remember? And I can't really optimize over discrete things very well. Okay, so instead I'm going to change this a little bit. So it's going to be, let's go from -1 to +1. So into a real function. So it goes from any real value, but it's going to snap it into -1 or +1. And so most of the value is going to be near -1 or +1. Sometimes we'll get something in between, so I'll be able to take a gradient, but I can't always do that. Okay, and Okay, so I'd like to be -1 or +1, but sometimes people use these other kind of ranges instead. So it's going to be or 0, 1, or say 0 to infinity. Actually, you have to use an open range for infinity. Okay, so it's mapping to some other sort of range, but think of it as kind of morally like trying to be -1 or +1, but it kind of has round it. Okay, so let me describe the rest of the network, and then I'll give you a sense of what these activation functions are. Okay, so now I've got this input again. Now, so I've got a hidden layer, and I'm going to build the same structure on top of this, right? So I'm going to look at building another neuron, starting with this hidden layer's input. And this is going to give me A2 I, okay? But I'm going to do some number k of these again, right? So this is going to be A2, 1, A2, 2, all the way to A2K, okay? And then I'm going to do some sort of phi function here again. That's going to pass through here. And the output is going to be a second hidden layer, H2, which is going to again be, say, of RK. I can use a different value. This could be K1 and this could be K2. It could be different sizes here. And I'm going to repeat this structure until typically at the very end, now I'm going to put a single neuron, right? This is going to be one final, final, say, classifier. Okay, at the very end of a single thing, and this one can have a threshold, and this one will output either -1 or +1 at the very, very end here. I can then do, is it greater or less than some threshold? Okay, so I finally do the threshold at the very end, but in between I'm kind of doing these soft thresholds that are kind of gluing it together. So I'm going to be able to take a derivative through this whole network here, right? So I'm going to have basically, this is one matrix, this is another matrix multiplied 2, right? W2 here, and I'm going to get W3 up to W4, and then I'm going to finally get some dot product at the end. Okay, but in between these matrix multiplies, I'm going to do these activation functions, which are going to kind of do something like thresholding, but kind of a soft version of thresholding. Okay, where think of that as there are all these neurons in there that have a decision, do they fire in the next round or not? And that needs to be a differentiable decision. Okay. Okay, so this is a nice organized structure. I'm going to have these set of these layers, and each layer is going to be a matrix multiply, then an activation function like a soft thresholding. Then I repeat this a bunch of times. The brain is not this organized. It's not if you talk to someone who works in like neural imaging, they'll say, oh, it's not a mess in there. I understand the structure. There's this kind of a cortical thing, whatever that, and this part controls language and this, and it all routes in this way, but it's not this organized, okay? And I've looked at a little of that research. I think it's kind of a mess up in the brain compared to this structure. This is very organized. This is a fully connected network. Another thing about actual deep neural networks is that they might have a bunch of these channels, but they're going to kind of, in fairly clever ways, leave out a bunch of the weights. They're going to fix those weights to 0 effectively and leave them out of what they're trying to learn. I'm going to say, I don't think there should be all the weights at every layer, and that will enforce some structure on it in certain ways. And maybe I'll talk about that a little bit at the end of the lecture. But that goes a lot in the design of how you set these up and how you choose to kind of look at a subset of the weights instead of all the weights, how big to make the layers. You do some, you'll do some weird things like adding some like long chains of weights to kind of connect stuff that's very far away ends up being important. Dealing with, and there are a bunch of kind of subtle issues that goes into this. And there's a lot of engineering now, right? So if you work in this, you kind of need to think about how to assemble these tools together towards a thing. And there's kind of an art to it that's starting to become a science, but it's still kind of early on. Okay, so maybe I'll come back to the big structure a little bit. But what we have not discussed yet that I need to discuss is what are these activation functions? Like, what are these things doing? Okay, so let's talk about these activation function. Okay, and so, so think of this as the goal is I want it to be a proxy for g of x, or let's say some f that goes from r to let's say +1 if greater than 0 and -1 if less than 0. I want to do something like this. I want to do something like a hard threshold function. Okay, but so this is 1, but I also want it to be so differentiable. Okay, so I need to be differentiable here so that it's because I'm going to end up doing something like gradient descent. Right, I said everything uses gradient descent. It's going to use it in this case, so I need to be able to take a derivative and kind of like this big delta function that we looked at for loss functions where we wanted to count the number of misclassifiers. That was not differentiable. It was not convex, had all these sort of issues. And that's the same thing here with the threshold function. So I want to somehow create something that looks kind of like the threshold function, but is kind of is differentiable in a way. Okay. Okay, so I'm going to give you kind of 3 common options here. Okay, so first one's called the hyperbolic tangent, and this is that's where I've taken a phi of a, and the output is, you can sometimes see this as tan h of a. Okay, if I write tan h, and this is this kind of weird expression minus y, or minus a e, so e to the a minus e to the minus a divided by e to the a minus e, or plus e to the minus a. Okay, and this will give you something that's in -1 to 1, and it basically looks, so I'm going to have 0 here, and it's going to do something like this, right? So where if it's less than 0, I'm going to give a function that's very close to 0, and if it's right, so think of there's this line here, this is 0, this is 1, and it's going to kind of very sharply go up and then go to 0. So if I'm anything that's kind of any value of a here, right, any value of a which is greater than 0, it's going to map to something almost basically 1. If it's less than 0, it's basically going to map to 0. And it's going to be differentiable in between. Oh, so sorry, this is mapping from 1 to -1. Sorry. Let's try and fix this. Okay, so this is like -1, and then 0 is going to go through here. Yeah, so this is like 0, 1, and -1. Yeah, so if A is now less than 0, it's going to map pretty closely to -1, or if it's greater than 0, pretty closely to +1, and it's going to be differentiable in between. Just kind of trust me on that. I'm not going to write it down, but you can work out, or you can look up the derivative of this function, and it's well defined, so you can write it in code, pretty easily. It involves exponentials, so it's kind of maybe a little bit slow and stuff, and a little bit messy, but you can write this up, and it's differentiable, and it kind of is forcing this kind of snapping to something like -1 or +1, firing or it's not firing. Okay. Okay. So if you want to go to -1 or +1, this is a good option. So something that's more common is a sigmoid function. Okay, the sigmoid function, okay, is instead is a little bit simpler. This is e to the a over e to the a plus 1. Okay, and this instead is going to give you something between 0 and 1. And this is going to do something fairly similar here, where except it's mapping between 0 and 1 here. This is 0, this is 1, right? This is a greater than 0, this is a less than 0, right? So this is mapping between 0 and 1. Think of 1 is firing, 0 is not firing. Actually, this is a little bit more intuitive than -1 or +1. We use that for classification, but intermediate step, this actually makes more sense. So either it fires or it doesn't fire. It's a way of thinking about it. But again, it's differentiable as kind of doing this soft rounding of this soft thresholding of what's going on here. Okay, and then so this is kind of completely smooth. Think of it kind of like a parallel to the logistic regression. This is kind of the smoothest way of having these soft 0-1 thresholding. Okay, what's even simpler, and it's kind of like the hinge loss, is what's called a ReLU, a rectified linear unit. And this is more like the hinge loss version of this. Okay, and this one is going to be the max of 0 and A. Okay, and this is now between 0 and infinity, right? So this can still have arbitrarily large values, and I'm basically just passing through the value if it's greater than 0, but if it's less than 0, it's going to be exactly 0 here, right? So this is going to have, this is the 0 function, and so this is going to look like if it's less than 0, it's going to return exactly 0, and at this point, it's going to be a straight line. But this can go up to infinity. A greater than 0, a less than 0, it maps to 0. Okay, so otherwise it would be negative, but I take the max of 0 in that value, right? So this is called a ReLU, and this is another way of effectively, it's not really rounding at the top. I can get the values to be big, but it's going to be 0 if it's small enough. And this is the advantage that basically if the sum of the inputs times the weights is less than some threshold, right, then it does not send an output signal at all, right? So there's nothing coming out of that neuron, and it kind of sparsifies the signals as they come through, and you can think of it that way, right? Whereas the sigmoid kind of rounds stuff to 0 and 1, but it's never really exactly 0, right? It keeps its differentiable everywhere, whereas this one has a point that's not differentiable, but I can kind of just pretend the derivative is 0 there. Where this sigmoid is differentiable everywhere, I don't need any case statements, but it's not exactly sending signals all the way to 0. They become just very, very small. Okay, so these are the most common kind of activation functions, which are kind of these elements that are coming here and they're acting like this thresholding within this network. Okay. Okay, so this is the basic, understand the structure of the neural network. What you basically, you fix the connectivity where you can have weights, and then you do these matrix multiplies with thresholding in between, and you fix the thresholding effectively in between. And it's usually just this feed-forward neural network. I mean, there are all sorts of varieties. There's these Siamese neural networks, or there are these GANs that kind of have more complex structures here. If you take a deep learning class, you probably learn about some of these cool extensions of this. Okay. Okay. So how do we learn this function, right? Before, we were able to show that these functions were over the parameter space were going to be convex, and we could set up a gradient descent formulation, and I kind of explained to you the gradients were pretty simple to take. Now this big chain complex things together, and it's a bit trickier to understand. Okay, so so a kind of the neural network function. Okay, so again, we're gonna use gradient descent here in some way again, and this means that we need this function g of x, right? Remember, the first input layer was this input stuff here, x, right? It was still this points in RD. Okay, so we're still going to have that. We still have a function of x, right? But instead, this function is going to look like, I'm going to write it from the backwards forwards. I'm going to take x and I'm going to multiply it by this first matrix, W1, right? That was the first layer. Remember, instead of a dot product, I've got a bunch of dot products stacked on top of each other. That's a matrix multiplication. Okay, so I'm going to take this output. This is the output of the first layer, but then I'm doing this activation function, and I'm doing this kind of soft thresholding. Okay, and then I'm taking this again is going to give me a vector, right? So then I'm doing a matrix multiplication with the second layer, W2. Okay, and this is the output of the second layer, but then I need to do again a soft thresholding of this. Okay, and I'm gonna keep doing this, and I'm gonna keep applying these layers until I have the second to last layer, L-1, right? And this one is gonna be final the soft thresholding, right? And then I'm going to do the last layer here, WL. And this last layer might only be, that simplified things, this last layer might only be a single vector weight function, right? The last one is basically just a perceptron at the end. So this might be a lowercase w. Okay, and this is my output function. And then maybe I can learn, say, minus b plus, right? So there's maybe some threshold. Okay, so this is what the function looks like. Okay, and now I've got it's like before, but now I have a lot to learn, right? What parameters do I have, right? These are all of the parameters, and this one is d times k1. This one is k1 times k2. This one is k L minus 1 times KL minus 2. You know, this one is k L minus 1, right? So the total size, and this one is 1, but so the number of parameters is going to be the sum of all of these things. Okay, so there's a huge number of parameters now. Okay, and okay, so your first concern from what I taught you in this course, okay, what is the most important thing about this? Well, okay, before we even talk about learning this, right? The first concern should be that's so many parameters. That means it's a complex model. That means we might be overfitting the data. All right. If you remember polynomial regression, similar thing with polynomial classification. If you have too complex of a model, you may be overfitting to the data that you have. Right. So you could be fitting something that basically is interpolating through all the data points, like we did with polynomial regression. But when you get new data points, it might not work, right? And in fact, people have looked at it. When you train these neural networks, these deep neural networks with huge numbers of parameters, they are kind of interpolating the data. They're learning maybe it's not regression. Maybe sometimes you can use this for regression too. You don't just have to do classification, but you could do neural network for regression too. And then it really is basically interpolating what the data is. Yeah, so that should kind of be a warning flag. And so kind of neural networks has had this history where the first idea of the neuron was basically one of the first learning algorithms. And then people are like, well, it can't learn very complex things, right? It can only do basically linear classification, right? And then people found, well, if I put just two layers, I can do much more than linear classification, it turns out. If you make two layers and you make the hidden layer, just the second layer H big enough, you can learn any sort of function, right? If I make K large enough and I just have this one hidden layer and then another neuron on the end, I can learn any function. I need to make K very big. And so again, I'm getting lots and lots of parameters. Same way, polynomial kind of classification with the degree high enough can learn anything. And so, okay, so you could learn stuff just like polynomial classification or kernel classifiers. But there were, well, it's so many parameters. How do I know how big to make it? And how do I ensure I'm not kind of overfitting onto the data? And so it kind of was slipped out of the mainstream of machine learning. People are focusing on these kernel techniques because they knew they were convex and I could learn them efficiently and they could prove things about kind of various accuracy guarantees in certain ways. They couldn't do that for neural networks, and kind of a fairly small group comparatively of the research community kept working on this and making networks bigger and bigger. And finally, the amount of data we've had has just kind of exploded in the last 5 or 10 years. And people said, well, let's try building big networks with this big data. And they started just working. They work better than anything else, right? And this was kind of, so some people from the more kind of mathematical side said, I don't believe it, right? Must be overfitting. I don't believe what's going on, but they used cross-validation and they had a held out set, and they are working. They were working better than everything else. And that basically continues today, in addition to sometimes these random forests work a bit better and stuff like that. But these overly complex models are now working well. So this is kind of confusing why it's working. It turns out that there are lots of these little tricks you have to worry about when optimizing these, and you worry about the structure of it in some clever way about these networks, about you don't make these full matrices in ways that tunes to the type of data that you have, right? And you do things like when you're optimizing, you'll leave out certain things, or you'll start with all the weights being 0. And this kind of tends to bias it towards simple solutions in ways that we've come to kind of understand over the last 10 years or so. And this kind of has regularized it, kind of adding a prior. Think of a regularization as like adding a prior onto your model in some way. And it's kind of like adding a prior towards a simple model in various ways that implicitly does that, which I'm not going to really cover in the last 10 minutes. And that's allowed it to kind of generalize fairly well in ways that we're kind of understanding now at this point, kind of not really understanding, but it's doing what it's doing. So yes, okay. So that's one thing I want to say. This is the formulation, and so I can think of now. I want to turn all of these things into these these parameters, which are going to be an R number of P, right? There's effectively some vector of parameters alpha that I want to optimize. I want to solve for the best parameter choice there. I need to figure out how to do this. This is the other key point. How do I train this, right? The decision trees and KNN neighbors, I didn't really have to train. With the kernel SVM or regular SVM, I could run gradient descent, right? The answer here is going to be to run gradient descent. In fact, they're going to run stochastic gradient descent, version of the stochastic gradient descent, because these make sense on very, very large data sets. Okay, so, but in order to do that, I'm going to get this function, so g of alpha of x, and I need to take the derivative of this. I need to write, the key thing I need to do is g of alpha of x. I need to somehow take the gradient of this function. Okay, and this is done through a technique called back propagation, which is what will allow me to do this. And I'm going to try and explain this in the last 8 minutes of the semester. And I'm not going to be able to fully write it down, but it's basically, you could write this down and try and just take the derivative of everything. And it turns out that's too computationally intensive. Backpropagation allows you to kind of do this in a way which is fairly efficient. And it basically does it layer by layer. That's going to be why the layers are so important here. Okay, and so I'm first going to write this down, the kind of the gradient. You basically first solve for the gradient for, let's say, this layer first. So I'm going to write the gradient, but I'm going to write the gradient of, this is alpha, of basically of WL of x first. Okay, and the idea is that if I look at the output here, this is going to give me a hidden layer HL, or H, maybe this is HL minus 1. Okay, so this is going to be the last hidden layer. And the last hidden layer, and if once I've passed data forward to, so how am I going to compute this gradient? I'm going to basically do it in 2 steps. One, I'm going to compute g of x on a data point, right? I'm gonna use the decomposable function. So for each data point, I'm gonna compute the value, and then the gradient will be a sum of all these. Or if I do stochastic gradient descent, I just need for this one data point. So I'm gonna compute for the one data point, but this is actually gonna have 1a. I'm gonna compute basically the first layer, the first hidden layer, h1 of x. Then I'm going to use this to do 1b, which is going to be compute the hidden layer, the second hidden layer of x, which is actually going to be of h2 of h1 of x, right? These layers pass forward in this nice structured way up to 1L, which I'm going to do L minus 1. So step 1L minus 1 minus L, I'm going to compute H, the last hidden layer, which is the kind of the last, right? So I'm passing this forward, and I'm going to pre-compute, store each of these layers, and then 2, I'm going to compute the gradient, but I'm going to go backwards now. So 2, 1, I'm going to compute the gradient with respect to the last layer, right? And this is going to take in the value x, its corresponding label y, which is going to tell me to go negative or if I misclassified it or not, right? And then it's going to take in the last hidden layer, right? So this is 2a, and then I'm going to go backwards. So I'm going to compute from the left to the right all the hidden layers, and then I'm going to compute the gradient backwards, the weights that are in each of these red kind of layers of neurons, these matrices. I'm going to go from the last layer back to the first layer. Okay, and so what's nice here is that once I have, because I've computed this forward, I had the hidden layer L minus 1. Actually, this was, let's say this was green. Right, so I had the hidden layer. This is HL minus 1. Okay, and then I had the kind of the X. All right, I had basically G of X1, and I also had Y1, right? So I'm going to get this ZI value, which is going to be YIG of XI, right? And that tells me, remember, I wanted, I'm going to put a loss function on side of here. I have a loss of ZI, and that gives me a gradient on here of each of the weights in this layer, right? So then I can compute a derivative the same way I did if I was learning a linear classifier, using a loss function like only this last layer I put a loss function, and I'm using like the sigma or the logistic loss function or the hinge loss on here, and I can take, and this learning the first layer is just like learning a linear classifier. Okay. Now on the second to last layer, right? So now I have HL minus 2, and I have H of L minus 1, right? And sitting inside of here are a bunch of these neurons sitting inside of here, and each of them has a weight function. This is L minus 2, say J. And let's just look at learning one of these things, right? Now, instead of this, I also had this I have this activation function that's going to work like the loss function. So now the gradient of WL minus 2J, right, at some x, y, right, some data point. This is somehow going to depend on, I've computed the gradient function here, so this was in step 2, say 2.1, the first step that I did here, and I'm going to use that passing through this activation function in place of Z, right? So instead of a loss function on ZI, I'm going to use this activation function times the gradient at this point would be HL minus 1J, or let's maybe I'll call this one I, different from J. So it's the gradient at H L minus 1 I, right, for the ith. Yeah, so this was also I here for ith here, and this goes from 1. Right, so I'm going to learn these weights here. I'm going to replace this, how I use this loss function on the zi with the activation function on the gradient here. And that's going to be able to calculate the gradient for everything inside this weight. And I can kind of keep doing this backwards and learn all the weights. Okay, so I pass forward to calculate all the hidden layers. And then it turns out I'm going to compare the results of those hidden layers with what I'm getting out of the gradient and the derivative, and I can compute through this technique called back propagation all of these values. And it's kind of ultimately it's a very complex, or a very useful version of the chain rule of taking derivatives. And you can write down these derivatives are going to be just the product of all the derivatives that come after them that in the network. And you take the product of all those things and you get the derivative at each of these weights, internal weights. And the calculation ends up being some form of dynamic programming, which hopefully you've seen in one of your algorithms class. Okay, so I didn't get to fully explain that. It's the notation is very heavy anyways to really understand all the details. I think I've done an okay job in the book. If you want to look there, there are some tutorials online that I can link to if you're interested. Although the notation gets kind of heavy, so it takes a while to walk through. But hopefully you've gotten the big intuition. You can write down the derivative through back propagation, and then you can run gradient descent or stochastic gradient descent. It turns out this is not convex. It's not a convex function, but if you run gradient descent, it finds a local minimum, and that usually works pretty well. They usually do lots of random restarts, like we did with Lloyd's algorithm for k-means clustering. And they throw randomness in there in various ways, so you don't always get to the same solution. You may rerun it a couple times. And there are definitely issues with doing that for machine learning, but this is what people use. Okay, hopefully you got a good sense of how these neural networks work, and kind of in general, the landscape of machine learning. But I think I'm gonna stop here. Okay, so I'll move to office hours if you have any questions. It's been a pleasure this semester. Hopefully you enjoyed everything in the class. And there'll be a review session on Monday if you want to kind of get more prep for